Section 6.5 is log properties. Log properties. So I want to tell you, in fact, let me just go to a fresh screen here. Let me give you 6.5 log properties. Let me give you the 3 properties that are important when it comes to logarithms. 3 main properties. The first one is that the log base b of x plus the log base b of y is the log base b of x times y. The second property is that the log base b of x minus the log base b of y is the log base b of x divided by y. And the third property is that the log base b of x to a power, that power can come down to the front and multiply. So those are the big 3 log properties. So these properties, let's talk about them. Notice they all have log b, etc. They all have log b, so the b doesn't matter. The b is just glued right to the log word. Don't worry about the base. The base, we're not messing with the base. But what we're doing right here is we're saying adding becomes multiplying, right? Adding here, adding becomes multiply, doesn't it? So adding for 2 logs becomes multiplying for 1 log. And then down here, subtraction for 2 logs becomes dividing for 1 log. So notice, which is an easier operation? Adding or multiplying? Which one's easier? Which one did you first learn when you were a kid? Adding, right? So in other words, the easy operation for 2 logs becomes the harder operation for 1 log. The easy subtraction becomes harder division for 2 logs. So an easy way to remember this formula is, you know the old saying, if two people work on something, it's easier, right? So if 2 logs work on something, it's easier. If one person has to do the job, that makes it harder. That makes it harder. So in other words, the easy operation is always for the 2 logs, and the harder operation is always for the 1 log. A job is easier for 2 people. It's harder for 1 person. So that's an easy way to help you remember that situation. And then down here, this just means power goes down to the front. Okay, so with that in mind, let's go back. So question number 1. We're having this situation, and they want us to make this, combine this into a single log. So let me write this. 3 log 2 plus 2 log x. There we go. Okay. Well, what do we do with these numbers in the front? Let's look back at the properties here. So the numbers in the front, those go back up to the power, don't they? So this goes up to the power, and this goes up to the power. So it becomes the log of 2 to the 3rd plus the log of x to the 2nd. And then adding for 2 logs, that's an easy operation for 2 logs, becomes, this is easy, this is an easier operation. Adding is an easier, right? Like when you were a kid, adding and subtracting were the easier operations you first learned when you were a kid. Multiplying, dividing, when you got a little older, that was harder operations. So an easier operation of adding becomes multiplication harder for one log. See how it became one log right there? It got harder for one person. So a job that's easy for two people, two logs, becomes a harder operation, multiplication for one log. And now, last thing, well, no, actually, that is the last thing. That is the answer. Boom, there it is. 2 to the third times x squared. There's our answer. Let's try number 2 here. So again, we have an easier operation, adding, for two people. It's going to become harder for one log. Now, see the log base 3, that never changes. In the last problem, we didn't have a base on the log, which really means it was 10, but we didn't need to show it. It was an invisible understood 10. On this one, the log, they both have log 3. So we're never going to change the log base. That just always stays the same. And now we're going to say it's a times, let's do it this way, it's going to become a times a plus 4. Because it becomes multiplication, becomes a harder operation. Multiplication, right? Adding, subtracting are the easy operations. That's what you first learned when you were a kid. Adding, subtracting, those were the easy operations. Multiplying, dividing were harder. You'd learn those when you're a little bit older. So it's an easy job just adding for two people. It's a harder job for only one person, only one log. It's multiplication. And then we can distribute that, a, because it's multiplying. So this will be log base 3 of a squared plus 4a. There it is. And we need to put parentheses around this. Log base 3 of a squared plus 4a. There you go. Let's try number 4. What do we do with this number in the front? He jumps up to the power. So this will become log base 3 of 3 plus log base 3 of y to the third, or fifth. Oops. Y to the fifth. That jumps up to the power. And now, an easier job for two logs becomes harder. Notice they're both log base 3, so that doesn't change. It's going to be harder. It's going to become times for just one person. It's harder for one log. Harder operation for one log. Easier, just adding for two logs. Easy job for two logs. One log, only one log. It's harder. It's multiplying. Multiplying, dividing are the harder. So there it is. There's the answer. You don't need to show the dot. You know, the dot, I'm just emphasizing it just to be super clear. But you don't have to, you can just write it this way. That means multiply, doesn't it? That means 3 times y to the fifth. So you don't have to show the dot on that. Okay. Next one. So again, we are, these numbers in the front go up to the power. This is natural log, but it's the same issue. Nothing changes. Whoops. It's going to be ln of w to the 6th plus ln of y squared. So the numbers in the front go up to the power. And then this is, again, easier job for two logs. It's going to be harder. It's going to be w to the 6th times, right? That means multiply. It's harder for one log. It's multiplication. Right? There's a times. You don't have to show the dot, but I'm just trying to be clear. It's multiplication. You don't really need to show the dot. It means multiplication. There it is, as they show right there. Okay. Let's try number 5. So again, what does the number in the front do? Goes to the power. Goes to the power. So log base 2 of y to the 19th minus log base 2 of w squared. Now subtraction, that's again an easier operation. Adding and subtracting are the easier operations for two people, two logs. It's an easy job for two logs. But now I'm going to make it one log. Log base 2, log base 2. They're both log base 2. They got to be the same. They are the same. We make it one log base 2. Now, easier subtraction. Remember, adding becomes multiply. Right? Back over here. Same thing here. Adding becomes multiply. Let's look at the properties. Adding is connected with multiply. Subtraction, that's connected with dividing, isn't it? Subtraction, right? Because subtraction and dividing both makes things smaller, whereas adding and multiplying both make things bigger. Subtraction leads to division, or vice versa, division with subtraction. Okay, so back to it. Here we are. So this is going to be, it's going to become divide here, isn't it? It's going to be y to the 19th over w squared, like that. Becomes divide. It's a harder operation for only one log. It's a harder job for one person. It's divide. It was an easier operation, just subtraction for two logs. Number 6, same kind of thing. These numbers go to the power. So what are we going to get? We're going to get ln w to the 10th plus ln z to the 13th minus ln x to the 13th. Now, we're going to combine them into one ln. So these are easier operations for 3 logs, right? You know, it's the same for 3 people. It's an easy job. It's going to become a harder operation for only one log. Be w to the 10th times z to the 13th, because that's adding, leads to multiply, divided by x to the 13th, because that subtraction leads to divide, and then put parentheses around it. Whoops, I kind of scribbled that one up there. And there we go. Just like that. Same principle. Okay, now down here on number 7, again, these numbers in the front go to the power. So this will be log of z to the 1/3. Now, here's the trick. You have to know what a fraction power means. So let's go back to a place where we have a little more room right here. And let's write in some important properties. Fraction powers lead to roots. So if you have like x to the a over b power, the b swings around and goes in the hook. The a stays where it's at. Write it like this. There we go. Right? The x to the a, that doesn't change, but the b swings around and goes into the hook. That has nothing to do with logs. That's just what fractional powers mean. They turn into roots. The denominator swings into the hook. Right there. It's called the index of the root. Let's go back then. So, that means this is equal to log. Now, what does this 1/3 do? The 3 swings around, becomes, whoops, got to write a little bit better than that, becomes the 3rd root of z to the 1. See how that 3, the denominator, swings into the hook? And, last step, you don't need to write z to the 1, just write z. Z to the 1 just means z. There we go. No need to write that 1. Anything to the, there's an invisible 1 power already understood to be there. Number 8. So now we're going to do the same thing, but we're going to go the other way. We're going to start from one log and break it into several logs. So I'm going to say, okay, this is understood multiply right in there, right? It means multiply. So that's a harder multiply is a harder operation for one log. I'm going to make it easier. Log z to the 13th plus log y to the 13th is going to make it easier adding for two logs. So it's the easier operation for two people. And then you know what those powers do. So multiplying, a harder operation for one log, became adding, easier for two logs. Adding is an easier operation than multiplying. And then you know the deal, the powers come down to the front of whatever log they're on. So this will be 13 log z plus 20 log y. There we go. Just like that. Okay, let's try this one. So this is 1 log. So it's a harder operation. It's dividing. It's a harder operation for one log. It's going to become easier for two. So it's going to be the log of z to the 16th. Dividing connects with subtraction, So that becomes easier. Subtraction's an easier operation. Easier for two logs. Easier job for two people. And then we cannot leave those powers. The power is going to drop down. 16 log z minus 7 log y. There we go. There's the answer. Put parentheses around these guys. There we go. Same thing on that last one. So do you see what we're doing? We're just running these properties forwards and backwards. It's all we're doing. Forwards and backwards on the properties. So we're just saying, what does it mean this way? What does it mean that way? So forwards and backwards on the properties. So they give me 1 log. I break it into 2 logs. Here again, 1 log. I break it into 2 logs. Back over here in 6 and 7, they gave me 3 logs, and I combined it all into 1 log. Right? So I just keep doing the properties. Number 10, 1 log. They want sum or difference of several logs. So 1 log, make it several logs. Okay, we can do that. So this is dividing. It's harder. That's a multiplying and dividing are the harder operations. Harder for 1 log. So I'm going to make it an easier operation. I'm going to make it subtraction for 2 logs, right? Dividing becomes subtraction, which is an easier operation for 2 logs. But that's not all. This really means 6 times y here, doesn't it? These are 2 items inside of 1 log, so I can break that up into 2 logs with an easier job for 2 logs, right? The harder multiply becomes the easier add for 2 logs, and then just keep that back part the same. Put our parentheses on these guys, and there we go. So do you see how we just kept breaking it apart? Dividing became subtraction, and multiplying 6 times y on the top became adding of 2 logs. On the bottom, same kind of thing. We have 1 log. They want me to make it a sum or difference of logarithms. So let's do it. So it's going to become log of x to the 15th plus log of y to the 15th. Because that's understood times on the top. Times becomes adding, becomes an easier operation. It's easier for 2 logs, harder for 1 log, and then after that we have divide by the z to the 17th, so that becomes subtraction. Again, easier because we're breaking it into 2 logs, log of z to the 17th. Do you see how multiplying on the top becomes adding? And then dividing by the z stuff becomes subtraction. Easier operations, just adding, subtracting, easier when you go to several logs. Harder, multiplying, dividing are harder operations for one log, multiplying and dividing. Okay, and then last thing, you know the drill. This power comes down to the front, this power down to the front, this power down to the front. You can see the answer right there. They just brought those powers down to the front. There you go. Number 12. Okay, so same kind of thing on this one. I'm going to make it several logs. So log y squared plus log z to the fourth. Okay, because this is multiply up here. That's multiply. That's a harder operation for one log. That becomes adding. Easier for two logs. Minus, this divide becomes minus log fifth root x plus 3. Now, where do we go from here? Well, this power is going to come down to the front. This power is going to come down to the front. No big deal there. But what about this fifth root? What is that? Do you remember that a root is the same, let me write this a little better, as a fractional power? Right? There's really a 1, so this is 1/5. What am I talking about? Well, remember this property back here. Remember when you have a denominator, when you have a fractional power, the denominator can swing into the hook, or the hook can go back to the denominator. Either way. It can go either way. In other words, those are two ways to say the same thing. It's kind of like me saying one or uno. I'm saying the same number in two different languages. You can have the power you can have the number in the hook called the index. This is the index of the root when it's there, the index. Or you can swing it into the denominator. Here it is in the denominator. It's the same thing. It's just two different ways of saying the same thing. A fractional power or a root. Two ways of saying the same thing. So get back to this problem. We can let this 5 swing back to the denominator. You might wonder, where's the 1 come from? Well, everything has a 1 power. If it's not showing a 1 power, it's got to be there. So the 1 power was invisibly there. The 5 from the index swings to be the denominator. Okay, great. So what? And then, what do you do when you have a power on something? It can drop down to the front. That's the log property 3. Let's go back here, right? Powers come down to the front. Powers down to the front when you're on a log, when you're a power on a log. So this part will become 1/5 log x plus 3, right, like that. It's minus. The other two, the 2 came down in the front, right? This 2 came down, plus, and this 4 came down, and then minus, and there we go. There's the answer. Okay, let's look at 13. 13 is similar, but a little bit different. On 13, notice we have this index 5 over the entire fraction. There's an invisible 1 power up there as well. So what that means is we can take this whole thing, x to the 4th, z to the 16th, w to the 12th, to the 1/5, right? You can take that 5 and swing it back there to the denominator, right? It's the root over the whole fraction, so it becomes the fractional power over the whole fraction. So far, so good, right? We can always swing from an index to a denominator power. A fractional power is the same as a root with the index number. And now, when you have a power on a log, it can drop down to the front. That's log property 3, right? Powers go down to the front. So this 1/5 goes to the front. 1/5 ln of x to the 4th z to the 16th over w to the 12th. Here, I don't need these other parentheses. Just put the 1/5 in the front. And now, next step, now we can break up the log. Right? Because this is multiplying and then it's dividing for the denominator. So it's natural log x to the 4th plus natural log z to the 16th minus natural log w squared. Or, I'm sorry, w to the 12th. I didn't see that little 1 there. W to the 12th. Now, there's one mistake I'm making. I got to put parentheses around all this. Why? Because that 1/5 right here was in front of the whole natural log. Therefore, when the natural log breaks into 3 natural logs, that 1/5 has to be in front of everybody. So the parentheses put him in front of everybody. Rather than, there's no parentheses and he's only on the first part, only on the x to the 4th. That's not right. The 1 to the 5th, the 1/5 was in front of the whole log. So when the log breaks into 3, he's got to be in front of everybody. So now, last step, we bring down the powers. So this 4 drops down, 16 drops down, 12 drops down, right? Because this multiplying became adding, dividing became subtraction, right? Easier operations when you break it into several logs, harder. It's harder operations here for 1 ln, easier for many. And we can see there's that answer when you bring those powers down. Okay, number 14. Which of the following are equivalent to log base b of 3? Choose all that apply. So this isn't just one answer. Choose all that apply. Well, having a keen eye, you're probably already seeing the answer down here. All of the above. Every one of these is the same as log base b of 3. Really? How could that be? Let me prove it to you one at a time. So let's start with this first one here. This is really a -1 in front. Okay, so what? Well, we're just gonna play with the properties here. Remember the property about numbers in the front? Powers go down to the front, or vice versa. So this number in the front can go back to the power. It can go either way. 2 ways of saying the same thing. So that -1 goes up there, right? You could bring the -1 back down, but we don't want to do that. We just put him back up there. Why am I doing that? I'm trying to show it's the same as log base b of 3. How am I going to do that? What is 1/3 to the -1 power? Do you know what that is? 1/3 to the -1 power. Do you know what that equals? If you're not sure, let me go over here and add it to my list of rules. It's an important rule. Negative powers. So what's up with negative powers? What's up with a fraction, say like 2/3 to the -2? Remember what a negative does on a fraction? It flips it. And then it becomes positive. So negative powers, they flip things to the other side of the fraction, then become positive. So negative powers, they're negative, they're unhappy. It's like somebody that's unhappy at their job. They're negative. They're unhappy. And so they flip to the other side. They go get a new job, and then they become positive person. They're happy afterwards. So it's my analogy, if that helps you. So a negative power flips the fraction, and then it becomes positive. That's what it does. You need to know that. Negative powers flip fractions and then become positive. So this negative is going to flip this fraction. to become, so right here it's going to be log base b. This will be 3 over 1, and then the power will become positive, right? And so what's that? Log base b of 3. 3 over 1 is just 3, and to the 1 power, that doesn't do it. 3 to the 1 is just 3. Boom. What did we just prove? We proved it's the same as log base b of 3. That's what they're asking. They're saying, which of these are just weird or fancy ways of saying log base b of 3? Well, we already know the answer is all of them. So we just proved that the first one is a fancy way of saying log base b of 3 because that negative power can go up here. That flips the fraction, and that's just log base b of 3. Let's try the next one. Let's prove it's true. Well, subtraction, an easier operation for 2 logs, becomes log base b. Harder, divide, right? It's a harder operation for 1 log. Easier for 2 logs. Becomes harder for 1. And then what's that? That's log base b of 3. See, 24 divided by 8 is just 3. See, this one also is just a fancy way to say log base b of 3. Let's try the next one. We're adding. Again, that's an easier operation for 2 logs. That's going to become harder, 1/10 times 30. Harder for 1 log. Just 1 log now, not 2. See, over here there were 2. Easier operation adding for 2. Harder for 1 log multiplying. Okay, so what's 1/10 times 30 for 1 log there? Well, you put, anytime you got a whole number interacting with a fraction, put it over 1. 10 and 30 can cross cancel. 3. It's log base b of 3 again. See, we're just proving that all these are just weird, fancy ways to say log base b of 3 using these properties. We're seeing how they can, in tricky ways, use these properties. Let's try the next one. What does a number in the front do? Goes to the power, right? That's log property 3. Powers can come down to the front or vice versa. So, okay, so this is log base b of 9 to the half. Okay, what's so great about that? Well, now that's log. What is the half power? What did we learn about fractional powers? What do? The denominator can swing to become the index of a root. A fractional power is a root, and the denominator swings to become the index. So this 2 will swing and turn it into a root, the 2 root of 9 to the 1. What's that? It's the square root of 9, right? 9 to the 1 is just 9. So this is just the square root of 9. And what's the square root of 9? 3. There it is again. It's again just a weird way of saying log base b of 3. See how all these are just log base b of 3 using all these fancy properties? Last one. 1/3 goes up there. Log base b of 27 to the 1/3, right? Numbers in the front can go to the power. You know the drill. This 3 swings into the hook. So it's log base b. Turns into a root, doesn't it? Of 27 to the 1. That's just 27. Now, what's the 3rd root of 27? Well, if you break it down with your calculator, it's 3 times 9, and 9 is 3 times 3. So that's going to be log base b of the 3rd root of 3 times 3 times 3, right? If I break it down, 3 times 3 is 9 times 3 is 27. This is just a 27, isn't it? 3 times 3 is 9 times 3 is 27. That's just a fancy way of saying 20. It's a breakdown of 27. Now, 3 in the hook. Remember, the number in the hook tells you the deal at target. Remember how roots work? If you have a 3 in the hook, it's a 3 for 1 deal. 3 3s inside sends 1 3 outside. Log base b of 3. This also is just a fancy way of saying log base b of 3. They're all just fancy ways of saying log base b of 3 using the properties. Did you understand that last one? 3 3s inside the root lead to 1 3. Why 1? Because there's a 3 in the hook. The 3 tells you it's a 3 for 1 deal. 3 for 1 deal. 3 3's inside, 1 3 outside. There we go. 15 and 16. Now this is use your calculator. So literally, oh no, actually I got to tell you a fancy rule, which you might remember. Remember log base b of a? Let me write that a little neater. In fact, that might be a good one. I don't know if we don't have any more room here. I'll just put it right here. That's equal to log a over log b. Remember how the base goes to the bottom and you can make one log into two logs? That's a special rule different than those other three properties. That's a special rule when you can let the base go to the bottom anytime you want. Like that. So, okay, so what? So then this is the log. Let me bring it down here and write it a little better. Log base 19 of 10. So the 19 goes to the bottom, log 19, and the 10 goes to the top, log 10. So you make it two logs. So it's a way of changing one log to why would we want to do that? Well, because you don't have a log base 19 button on your calculator. You have no way of doing log base 19. You just have regular log on your calculator. You don't have a base 19 unless you have some super fancy calculator. Most calculators don't have it. So you're not going to be able to figure out log base 19, and it wants us to use our calculator on this one. So you can't do it unless you change one log into two logs. And this is called the change of base formula. Why? Why is it called the change of base formula? Because the base was 19. Now look at both these logs have no base, which really means they're base 10. They're both invisible base 10, as we talked about. But you don't need to write that. They've changed their base. They no longer have base 19. One change of base formula, one log becomes two logs with a different base. Well, I should just leave it as change of base formula. So anyway, now you can hit the buttons on your calculator. Hit log 10, so on your calculator, hit log 10, close the parenthesis, divided by log 19, close parenthesis, hit equals, and you'll get this number right here, 0.782. All right, last one. They want us to take log of 1/10. Let me bring it over here. Log of 1/10. Now, of course, you can hit the buttons on your calculator, but they say simplify without a calculator. Somehow there's some way we're supposed to know how to do this without a calculator. First off, notice, there's no base showing there. Do you see that? Do you see how this log is missing his base? What's his base? What is the base when it's invisible? What's the understood invisible base? 10, right? If there's no base showing, it's always 10. When base is invisible, it is really 10. Remember, that's the understood invisible base. Okay, great. So what? Well, then this is log base 10. Now, here's the other trick. That 1/10, do you realize I can write that 10 to the negative 1 power? We're using these tricky properties again. I can write that 10 to the negative 1. Why? Because remember what we learned about the properties? A negative power makes it flip and then become positive 1, and that's just 1/10, right? 10 to the 1 is just 10. So 1/10 is the same as 10 to the minus 1. Remember, negative powers are negative. They're unhappy. They want to jump to the other side of the fraction. Then they become positive after that. So it's just regular 1/10. So 1/10 is the same as 10 to the minus 1. Okay, great. So what? Now, this minus 1, well, what would be the best way to do this? Yeah, let's, if we're wondering what this equals, right? So let me just say, well, suppose it's equal to x. Let's just say whatever it is, it's x. I'm going to give a right side over there. Now, remember how we change a log to an exponential? Remember how we've learned to do that? We just we get rid of the log, and we go base to that equals that. So bring it over here. So 10 to the x is 10 to the minus 1. Did you follow that? The base to this side equals that side. So this whole thing, we're calling it x. We're setting it equal to x, trying to find what x equals. Whatever x is, it's equal to the whole thing, which is the original question. So what does x equal? Look at this equation here. What does x have to be to make those equal? -1, clearly. That's the real answer. So that one was a little tricky. There we go.